Okay, so the question I posed is related to the Artemis project, the Artemis mission, which is in progress now, and we're very close within hours, one way or another. Of right now, the spacecraft will reach its maximum distance from the Earth, about 40,000 miles beyond the orbit of the moon. Okay. Now, they say it's orbiting the moon. Yeah, sort of. But right now, with the ratios that we worked out last time, the 1/80 times R1 squared over R2 squared. Okay. We find that the Earth is exerting 2-3 times as much force in the thing as the moon is. So, yeah, I guess it's sort of orbiting the moon because its velocity here, as it falls back toward the Earth, it's going to fall closer and closer to the moon, and then the moon's gravity is going to overcome the Earth's gravity, and it will loop around the moon. It's not officially orbiting the moon; it's actually orbiting the Earth-Moon system right now, and will continue to. At some point, the moon will become very dominant. But it's an interesting thing. Okay, got a lot of data. Then we're going to try to get the meaning of some of the data. And I haven't worked out this question, but I estimate the thing might be 360,000 kilometers. Actually, yeah, okay, it was. It's not right now. There's a point in which it's 360,000 kilometers from Earth. Okay, and it's moving about 2,000 miles an hour. Is the Earth's gravity enough to keep it from going forever? Or do we need the moon? That's a question I have in mind. Now, before answering that question, pose this question: 360,000 kilometers from Earth, how much kinetic energy is it required in order to never return? Okay. Now, to go back to the most fundamental thing in pre-calculus is the functions of which we build everything. There are 5 basic functions, 5 toolkit functions, whatever, on which most of pre-calculus is built. And in turn, most of calculus. And in turn, most of physics at this level. Okay? Now, those functions and their inverses, and there are a couple more that come in. Main functions: the exponential, reciprocal square, cubing, squaring. Okay, I think that was 5. And their inverses. Yep. All those functions are power functions. It's very simple calculus. Any power function, it's easy to do calculus. Okay, and exponential functions, it's easy to do calculus. And the inverse of every one of the 4 functions that isn't the exponential function. All those functions are power functions. Their inverses are power functions, just reciprocal powers. Okay. And right there, we start putting it together: composites, sums, differences, quotients, multiples thereof, and we get the functions that are going to govern most of the engineering here. Okay. At least the engineering, we're really going to have to understand the functions. We really have an advantage in understanding the functions. Okay. So you have this function. This is your reciprocal function. Here's your reciprocal square function. Graph looks similar, but this is more concave than this is. What's this have to do with gravitation? First thing you learn about gravitation, when I asked, somebody said, well, G big N little m over R squared. That's a very good answer. Even before that, it's the fact that gravity is a reciprocal square or an inverse square function. Okay. What are these? Notice I've got 1 over R squared here next to 1 over X squared. You just multiply 1 over R squared by big G big N little m. There you have it. Okay. What's this have to do with anything? Well, if you integrate this, integrate force with respect to distance, you get work. So you integrate 1 over r squared, you get a multiple of 1 over x. You get a work function. Okay? Potential energy function being the negative 1 over x. With a big G, big M, little m multiplier. So mathematically, that's where we're at. And it's based on these simple functions with these simple tables, which already show you pretty much everything there is to know about the function except the algebra. And the algebra is easy. And the calculus is easy. It's a power function. Okay. That's a context. And you really want to understand things within that mathematical context. So when you solve this problem, as I said, when you were still trying to find the question, 2 things: do this symbolically. Don't start crunching numbers. You lose track of what you're doing and why you're doing it. Okay. But it's also advantageous at some stages to evaluate the numbers and see what kind of quantities they're giving you. So you kind of balance that out. But work it out symbolically. So you have the symbols that can answer the question, well, if it's 370,000 kilometers, how much does it take? How much energy does it take to get from 360 to 370? Okay. Of course, you don't know the mass, but that doesn't matter. You're doing it symbolically. It's little m. Okay. And if it's at a certain proximity to the moon, well, you got a different big M, same little m, different r. Okay, everything works out the same. So what are your expressions? Okay, when you see a problem like this, you're not sure what to do with it. Of course, this is exactly what you did on the assignment indices. Okay, that's exactly what the assignment of gravitation is talking about. I mean, it's talking about 2 or 3 different things, but this is one. So it might be phrased in a way that's not familiar to me. What I say to do then is start with what you know. The most fundamental thing you know is Newton's law of universal gravitation. The next fundamental thing that you should know is that you integrate that to get the work, because you integrate force with respect to distance. Okay? And work is related to potential energy because these are conservative forces. So right now you've got a framework. You got one simple formula that you're familiar with. Another one that you can derive from that one or memorize if you want to memorize things. But you should be able to derive it in case your memory fails you. And it also should be kind of second nature. Relation between those 2 things. That's your working your potential or your force and your potential energy functions. You also know centripetal forces mv squared over r. Okay, which is related to circular orbits. You put that together from Newton's second law, you get the velocity and distance relationship. And that's just one simple little set of pretty easy algebraic manipulations, and you can describe a whole lot of stuff. Okay. Then there's a vector form of the force function, which is going to be relevant when the thing is out there, subject to the force due to the Earth and due to the moon. And that complicates the living daylights out of the shape of the orbit. I can't work that out. Okay, not off the top of my head. And I might have to do some serious review on Lagrangian mechanics if I want to do that. Okay. So I leave that to NASA unless they call me with a question. You have to take it real quickly. Okay. If NASA ever has to call me, we're doomed. But anyhow, there you got it. There's a very simple framework for all the questions we're going to deal with today. And we're going to be focused mainly on Artemis because it's exactly what we're doing. And it's happening right now. Very cool. Okay, so symbolically, write down your symbolic relations. You see a question, you know it involves gravitation, you know it involves forces and energy. Write down those relations. There are basically three of them. And then see what you can do with it. And of course, you want to see them not just as formulas, but as graphs with shapes and as concepts that need to be put together to answer maybe some straightforward questions and maybe some more complicated questions. Okay. Okay. So what we need is first, your force is the force of attraction, so you put a negative on there. Helps you keep track of your signs and stuff. You can fudge your way out of that, but then it's over a square. And then what's the work from R1 to R2? Go ahead and write that out in detail to make sure we've got that locked in. Write out the calculation. There's the integral. That equals this variable R1 is smaller, then you're going to be doing positive push down divided by R2. R2. We have this, okay? That's equal and opposite to the change in potential energy, because the change in potential energy is the work done by the net force. And incidentally, I just noticed somebody has a mask on. So whenever I wear a mask, anybody wears a mask. Otherwise, I just don't breathe. Okay. So this is this and this are just part of the fundamental toolkit that you've always got to know. You've got to understand why. Okay. So we get the change in potential energy. Okay, well, the change in kinetic energy required to never return, or the kinetic energy, sorry, required to never return, is just the kinetic energy that you change to potential energy to get there. Okay, so okay. The worst looking conservative that's ever been written. That all force is conservative. You could write this as this is basic conservation of energy with the assumption that you have no non-conservative forces. for non-conservative forces, then you should know what to, but here we go. This means that to get from here to from R1 to R2, you're changing kinetic energy. The equal opposite if you're changing potential energy, which is this. You know, I think I wrote that down backwards. That would be a negative down R2 is bigger than R1. So I wrote that down wrong. If you write out the integral, you'd be integrating the negative of this. So be big G big M times 1 over R evaluated. Right. Can't be right. Hold on a minute. I've got to sort it out. Okay, so I don't remember if that's what I had originally or not, but the reasoning is simply if R2 is bigger than R1, you got to do positive work to get there. If you divide big G big M by R1, which is smaller than R2, that's going to give you a positive result. And of course, the details of the integration. You got negative signs there. It's not that hard to keep track of in your head, but there are 2 or 3 steps in my head. Ain't that great with working memory right now. So, okay, so anyhow, we have this. Okay. And you ought to be able to check that out in 2 ways. You check it out by doing the integral, and then you check it out by whether it makes sense. And at least one of the things I wrote down didn't make sense. Remember the first thing or the last thing. I think that's why I wrote it down first, but I don't remember. Okay, so work to get from R1 to R2 is this. Of course, this is your change in kinetic energy. Okay, has to be equal and opposite to the work that's going to be done against it. Okay. And of course, you got this, which tells you you're changing potential energy, changing kinetic energy is equal opposite to your change in potential energy. You guys use the right U potential energy. So everybody understands what that U symbol means, so we can use it. Whatever to be consistent with what I use here. And I'll go ahead and call it LU. So I'm scrambling 2 different ways to see this because intuitively, you know that if you're this far from the Earth and you want to go away you're gonna need some kinetic energy or some thrust or something. Where the thrust is a non-conservative force, we don't have any non-conservative forces. Whole thing is framed, how much kinetic energy required to never return, and implicitly we understand that we're gonna coast. Okay, if we want to burn fuel, that's fine, if we have fuel. We really want to go for it. So again, intuitively, we're here. We have to have enough kinetic energy to coast. Just like if you got a cart went up an incline, you got to give it a certain amount of kinetic energy if you want it to get to the end of the incline. Okay. Now, if it's an infinite incline, well, you'd take infinite kinetic energy. You couldn't do it. In this case, it's gravitation with a force that rapidly decreases as you move away. So the rapid decrease allows you to go forever. If it was a 1/r, if gravity was a reciprocal first power, then the integral would be a natural log. Okay. And you have the natural log of R2/R1, which is unknown. Okay. Nope. Which means it'd be impossible. There wouldn't be enough energy in the universe to get even a large part of pure infinity. Okay, so in that case, we have this, now we have numbers. We can find a change in kinetic energy, but of course, with our kinetic energy, when we get to infinity. When we get there, better be greater than zero at any point along path from here to infinity. Our kinetic energy can never be zero because as soon as it is, we start falling back. Because the Earth, no matter how far away we are, still exerts a little bit of force. Now, in the real universe, there are other things that are going to exert force. We're just talking about an ideal case here. There it is. So that change in kinetic energy can better be the negative of the kinetic energy you have here. So we get KE2 . The kinetic energy minus the original kinetic energy. Change in kinetic energy. I've got my signs right, there's something wrong about this, but you change in kinetic energy. It has to be the negative, the kinetic energy is start with. Now something's wrong with these signs. So let's stop and sort that out. Because basically the kinetic energy you start with has to be greater than or equal to this. energy kinetic energy is final minus initial. So something's a little screwed up there. Okay, first place. Try to actually have room to write out this integral and I have this right. I didn't, so it wasn't. Okay, it is R2 here and R1 here, which is a negative change of potential energy. This is not the work you have to do from R1 to R2. Okay, this is the work done by gravity. And like I said, I can't believe I did that. Okay. Work done by gravity, which is equal opposite as a change in potential energy. Not the work you have to do. What you have to do would be the integral of this without the negative. But the integral of f of r has a negative in it and it gives you this. Okay. We just have to remember the change in potential energy is work done equal and opposite to the work done by the conservative force. So it's intuitively, yeah, get something that doesn't make any sense, but it makes sense. Okay, so as R2 approaches infinity, what is this approach? Now everybody seems to want to write an infinity down here. Okay, there's no such thing. There's no such thing as G big M little m over infinity. The limit as R2 approaches infinity. And this is by the theory of limits. Okay, I'm going to go over the calculus with you. Okay. But basically, calculus just says, well, we can always choose an R2 that's big enough to make this as small as we want to. Epsilon, or exceed some number of big M. Okay, all that from calculus. Okay, I can write it out for you. Probably would screw it up. Now I've got that screwed, but there it is. Okay, and the idea is simply again, what do you mean by limited infinity? It means you can always make this big enough that this is as close as you wish to the limit. That's what all the epsilons and all those big N's and so forth we're talking about. Okay. So important concepts. All right. Now again, get involved in a lot of these symbols, these symbolic calculations. Intuitively, you could just think, if I integrate the force that I need to overcome Earth's gravity from here to infinity, or from R1 to R2, I get the opposite of this. I get the R1 here and the R2 there. The work that I have to do. Work that's done by the Earth on coasting spacecraft. That's equal out. Potential energy as I move away from the Earth is increasing, right? Okay. This is a negative quantity if R2 is bigger than R1. You got a bigger denominator here than you got here. Negative will dominate over this. Okay. So its potential energy increases. R2 is going to increase. Whereas R2 increases, potential energy increases. So those are the signs. Intuitively, again, you integrate your force from here to R2, from R1 to R2, get this expression, and you let R2 approach infinity. Thank you for the right of delta. Often I find that people get confused about what U means, but I don't think it's that way. Okay. And it's the minimum kinetic energy required at R1. He's never returned. Okay. Now, use this analogy in my last class for different purpose. What do we mean by, this means we end up with zero kinetic energy, right? How can we end up with zero kinetic energy and never return? Well, it's because we never get there. We keep moving. We never fall back. So we approach a velocity of zero, but we never return. I stepped halfway to a ledge over there. Okay. And the ledge, say, is a 6-foot fall, which is more than I want to fall right now. Okay. Step halfway. Step halfway. Step halfway. Keep stepping halfway, never get there. In the same sense, your kinetic energy never does reach zero, but there's always enough to keep going. Make sense? Exceptional? Okay. Now I want to do the numbers. What's the velocity have to be? Kinetic energy is this, which is just what you need to overcome the potential energy. Potential energy increases by this. What's your expression for the kinetic energy? Okay. Kinetic energy one is 1/2 mv1 Which is big G big M little m over R1, right? Then it's one square. Okay. Okay, well, what do we know? First of all, we can solve for V1, right? That's easy. Now, when I write this down, I write V1 because you got a 0.1 and a 0.2. Implicitly, we're going from R1 and we're letting, we want to find the work done to get from R1 to infinite separation, okay? And that's why we take the limit as R2 approaches infinity. So R1 is where we start. And the velocity we should have there, we don't want to write that as V because V is variable. V1 is the specific velocity, and it only makes sense, right, of one subscript. We'd write another subscript, but then it'd be hard to match up with R1. We'd understand that this is velocity at this distance. Okay. Okay, so what is that? Work out the numbers. I'm really curious because I know how fast it was moving. And I haven't worked that out because I wanted to let you work it out. Used to write a little m next to big M. Obviously, little m divides out here. The velocity is independent of that mass. Okay, so at about 250,000 miles, V was about 2,000 miles an hour. Okay. Now, the latest I've been able to get, because this site's been down. Site isn't down, it's just not getting any information. And the latest information I had let's get the specific information, okay? At 247,028 miles. (2,002 miles an hour). The latest information I had was this thing was approaching its apogee at 267,691. If I remember, I better check. He was down to 1,693 miles an hour. That's right. If I transcribe the data correctly. That's always in question. Well, what's the change in potential energy between here and here? From here and here. What's the change in kinetic energy between this velocity and this velocity? Change in kinetic energy equal to opposite direction of potential. Just take a minute and think about how you would work that out. Okay, so how would you work this out? Well, I'll give you a little thing. Call this R1, call this V1. Call this R2, call this V2. What's the change? What's the expression for the change in kinetic energy? What's the expression for the change in potential energy? You could easily put the numbers in. You'd have to convert from miles per hour to meters per second and from miles to meters. But I'm not going to ask you to do the conversion. Just write out in symbols what you would do, and the rest is straightforward. Okay, to answer this question, you'd write out the expression for the change in kinetic energy on the left side, the change in potential, negative change in potential energy on the right side. Well, writing it out literally, the change in kinetic energy is 1/2 mv2 squared minus 1/2 mv1 squared. The change in potential energy is I don't put R1 here or here. Well, change in potential energy as R1 here. I mean, the potential energy has R1 here and R2 here. So one thing about the potential energy that your text tells you that I haven't really talked about is we measure potential energy with respect to infinity. When we did this, we have this. This is potential energy relative to infinity. It's negative, which means that to get from R1 to infinity, we have to do positive work. Okay. So well, there it is. Okay. Think it through, make sure you have it. I don't have room to write everything out, so I'm going to leave it at that. It's just using these basic principles, but being careful about the signs, which starting right here, I wasn't, which got me confused. Okay. I mean, I knew what signs things had to come out with, and they weren't coming out that way. I was getting that we had to start with the negative kinetic energy based on the assumption that I'd written that down right. Okay. Now, of course, you can always remember the formula for potential energy relative to infinity. Right here it is. Big red circle around it. And I think I've got my subscripts wrong here again, because my potential energy at R1 a change in potential energy is potential energy. I end up with minus potential energy I start with. So really, it's the same expression. But my change in potential energy is later potential energy minus the initial potential energy. Again, I don't have room to write it out, so think it through carefully. This is going to be negative, because V2 is less than V1. And this should be negative, because R2 is greater than R1. And we're gonna end up with this thing over R2 minus this thing over R1, which is gonna be negative, okay? Change of potential energy is positive, but the negative change of potential energy is negative. And you want to lock in this idea, which really comes down to conservation of energy. What I read. Here. Okay, now. Oh, geez, we're out of time. We can't do the fun stuff. Get into the. Okay, so when we do this, we're going to find that it's not so. This is a potential energy change relative to the Earth. Using this expression for potential energy, that's just the expression for potential energy relative to the Earth. This won't work. Because the Earth isn't the only source, no way you could read that word. The Earth is not the only source of conservative force. You got the moon out there. Sun's involved too, and so is the rest of the universe, but you can pretty much neglect all that, although NASA probably doesn't. You know, Jupiter, Saturn, Mars, Venus, maybe even Mercury. Making little differences. Depends on how close you want to shave this orbit to the moon. And how precisely you want to locate your landing point. Turns out it's impossible. That's why you have course correction thrusters. You can't actually predict it all. You don't know all the mass distribution within the moon when you get really close. So if you talk about approaching a landing site, you have to make little adjustments at the end, but you get as close as possible so you have enough fuel to make the adjustments. But you do have to take account of the moon. So again, just confining your attention to the force exerted by the Earth and the potential energy for the Earth doesn't give you conservation energy. Next time, I'll tell you how far it was from the moon. Here. And the mass of the moon, which is about 1/80th the mass of the Earth. It's 1/83, something like that. Okay.